Okay, let's dive in. We're looking today at, well, one of math's really big stories, isn't it?
Absolutely. And a pretty controversial one, too.
Yeah, the Abbasid conjecture.
Yeah.
And this claimed proof that sparked, well, what, over a decade of global dispute now?
A huge dispute. And the thing is, this isn't just about like abstract numbers floating around.
Right, not just theory for theory's sake.
Exactly. The Abbasid conjecture, it really touches the very heart of arithmetic, that fundamental relationship between adding and multiplying.
You mean the simple A plus B is C?
That's the one. And a solid proof. It can unlock so much. People talk about even a simpler proof for Fermat's last theorem, for large exponents anyway.
Okay, so let's break down the conjecture itself. The sources lay it out pretty clearly.
Yeah.
You need three positive integers, A, B, C, simple enough.
Where A plus B equals C, and critically, they have to be coprime.
Meaning they don't share any common factors besides one, like 8, 9, and 17 works.
Right, but not, say, 6, 9, and 15 because they all share a factor of 3.
Got it. Then there's this idea of the radical of a number.
Yeah, rad-n. That's just the product of its distinct prime factors. So you ignore the powers.
Like the example, radical of 18. 18 is 2 times 3 squared.
So the radical is just 2 times 3, which is 6. It simplifies the number down to its core prime ingredients.
Okay. Now the conjecture connects C, the sum, to the radical of the product A times B times C. So rad ABC.
And most of the time, C turns out to be smaller than this radical rad ABC.
But not always. There are these rare exceptions. The sources give that example. 5 plus 27 equals 32.
Okay, 5, 27, 32, they're coprime.
And the radical of 5 times 27 times 32, well, 5 is prime, 27 is 3 cubed, 32 is 2 to the 5th.
So the distinct primes are 5, 3, and 2. The radical is 5 times 3 times 2, which is 30.
Right. And here C is 32, which is actually larger than the radical 30.
Exactly. These exceptions tend to happen when the numbers involve high powers of small primes, like the 3 cubed and 2 to the 5th there. They're sort of arithmetically dense.
So what the conjecture basically says is that these cases where SIC is significantly bigger than rad ABC are incredibly rare.
Extremely rare. Formally, it uses this epsilon. For any tiny positive value epsilon you choose, there are only finitely many coprime triples ABC where C is greater than rad ABC, raised to the power of 1 plus epsilon.
Or using that quality idea from the sources, high-quality triples, where C really outstrips the radical, are finite. Almost all triples are low quality.
Precisely. It puts a fundamental limit on how surprising the sum C can be compared to the prime factors involved.
So why is this considered so important? I mean, most important unsolved problem in Diophantine analysis is quite a statement.
It really is. Diophantine analysis is all about integer solutions to equations, and this conjecture, it feels like it should be true. There's a similar theorem for polynomials, the Mason-Stothers theorem, that's already proven.
Ah, so it's like an integer version of something known.
Kind of, yeah. And that analogy makes mathematicians strongly suspect it holds for integers, too, proving it would suddenly unify a whole bunch of disparate results in theorems in number theory. It connects things.
Okay, now for the twist. Enter Shinichi Mochizuki. Brilliant guy, but known for being quite reclusive.
Right, based at RIMS in Kyoto. In 2012, he drops this bombshell, over 500 pages claiming a proof.
But here's the catch. It wasn't using familiar techniques. It was built on his own, entirely new and incredibly abstract framework.
Interuniversal Teichmüller theory, IUT.
Which sounds intimidating. The sources talk about Hodge theaters and completely different mathematical universes.
It's described as fundamentally different. Not just a new technique, but a whole new way of thinking about numbers and geometry, apparently. Very, very hard to penetrate.
Which leads us to the mission for this deep dive. Using these sources to figure out why this didn't lead to champagne corks popping, but instead to, well, confusion, arguments, and this breakdown in how math usually gets checked and accepted. We want to help you make sense of the key issues here.
And where are we now? Well, the consensus in the wider mathematical community, as the sources confirm, is that the proof isn't verified. It remains unproven.
The core sticking point seems to be this specific step, corollary 3.1 in Mochizuki's papers.
Yes, that's what critics like Peter Schultz and Jacob Stix focused on. They published a detailed critique saying there's a critical gap in the logic there, a fundamental flaw, they argue.
But Mochizuki completely rejects their criticism, right? He basically says they haven't understood IUT deeply enough to see why the step is valid within his framework.
Exactly. It's not like finding a simple calculation error. It's a deep disagreement about the validity of the foundational tools themselves, which is unusual.
Have there been attempts to fix it or bridge this gap?
There have been efforts. The sources mention Kriti Joshi tried an approach, but Schultz critiqued that too, arguing it essentially ran into similar foundational problems, just maybe phrased differently.
So it really feels like more than just a math problem. The sources paint it as a breakdown in the social process of science.
That's a key takeaway, I think. How do you validate something so radically new, especially when communication is difficult? Isolation, communication style. These human elements seem crucial here.
Leading to what one source called competing realities. One camp believes it's proven, the other is adamant it's not.
It really highlights that even in pure math, establishing truth isn't purely mechanical. It relies on shared understanding, communication, trust, things that are inherently social.
Is there any way out? Formal verification comes up, using computers.
Yeah, proof assistance. If someone could translate the entire 500 plus pages plus background into a language a computer could check step by logical step, that could settle it.
But that's a monumental task for something like IUT. Hasn't happened yet.
No, it's a huge undertaking. So what's really fascinating, I think, is what this whole saga tells us about how science, even math, actually works. Establishing truth at the frontiers is messy, it's fragile, it's social.
Which leaves us, and you listening, with a pretty big question, doesn't it?
It does. How does the scientific community build consensus, find truth, when it's faced with ideas so revolutionary they seem to break the existing language we use to even talk about them?
Something to definitely think about. If you want to explore this more, do check out the source materials.